I would first of all, I would like to thank the organizers for inviting me to this conference. So I will talk about Strauss conjecture for the wave equation, and first I will recall the histories of the Strauss conjecture and roughly speak of our joint work with Lan An, and also talk about some unsolved problems. So Strauss conjecture just means for semi-linear wave equation. You can say Cauchy problem. So the equation is like this. This is power p nonlinearity, and for convenience we put a worst sign. And this is the wave operator. So we consider small initial data. So it's Cauchy problem. So we want to know whether the solution is global. Global means for all time, and or solution blow up infinite time, which means solution become infinite time. So the work begins in 1979 by the later Professor Zhou. He considered the case that the space dimension is 3 and the initial data is compact supported. He proved the two main results. If p is greater than 1, less than 1 plus square root of 2, then the solution will blow up in infinite time. If p is greater than 1 plus square root of 2, then solution exists globally in time. For small initial data, we always consider small initial data. This implies that p equal to 1 plus square root of 2 is the critical exponent for the in the 3 space dimensions. After that, Strauss conjectured that for n greater than or equal to 2, the critical power should satisfy this equation. So when n equal to 3, this p is 1 plus square root of 2. But Strauss was previously studied nonlinear Schrodinger equations, and he discovered this equation. But the root of this equation is not the critical point for the Schrodinger equation, but then it turns out it becomes the critical point for the wave equation. So this is the Strauss conjecture. Then in 1981, Glassi solved the Strauss conjecture in 2 space dimensions, because Zhou showed in 3 space dimensions. So the 2-dimensional equation is studied. And then in 1984, Seidlitz proved that for n greater than 2 and the p is less than the critical value, then there is a blow up. So, this subcritical value has been completely resolved. And Seidlitz's work was later simplified by Ramaha and Zhou and Zhou, etc. Then Schaffer showed the blow-up result for the critical value, where n equal to 2 or 3. So the critical value also belongs to the blow-up. So then in 1995, I showed the global resistance for the supercritical value in 4 space dimensions. Then Lindebrand and Zhou was able to show it for n less than or equal to 8. Then finally, in 1997, Gergiev, Lindebrand, and Zhou would show the global resistance for p greater than PCN, n greater than or equal to 4. So the Strauss conjecture is completed except for the critical value. And their proof is The proof has two parts. One part is they study a weighted estimate, which they use harmonic analysis, and then another part is using Lorentz invariance. And so the proof is difficult. And in 2001, Tartalo gave a simple proof. Tartalo used a geometric proof. He transformed the wave equation in Euclidean space to that of the wave equation in hyperbolic space. His proof is simple, but he completely go to the hyperbolic space. So he used harmonic analysis and geometry in hyperbolic space, which is not known to large audience. So the remaining part of Strauss conjecture is the blow up in the critical case for n greater than or equal to 4. This was solved by Yudonov and Zhou and myself independently. So it's completely resolved. So we can also study other because Strauss conjecture is a wave operator, right? Wave operator can be replaced by other wave operator in other geometries. So people have studied the background is not Minkov space, but with a Schwarzschild space-time. Schwarzschild space-time is a solution to the Einstein equation. It's a radial symmetric solution to the Einstein's equation. So people also study this, so I believe. So also studying this kind of problems. Then let me see. So in 3 space dimensions, the Strauss conjecture for the Schwarzschild space-time was also, and even for Kerr space-time is also a solution for the vacuum Einstein equation with small angular momentum was resolved by Lindebrod and many people. So this was resolved. So we will talk about our work, recent work. So we consider a nonlinear wave. Our recent work is to give us elementary proof of the result of the Gergiev, Lindebrod, and Zhou. So we study this problem. So sorry. So we talk about this problem. So it's still this problem. The global existence for the supercritical case was established by Gergiev, Lindebrod, and Zhou. And another proof was given by Tartalo. As I said, the proof of Gergiev, Lindebrod, Zhou using using weighted Strauss estimate, and their proof has 2 parts. And first part is to use to study a weighted estimate, L2 estimate, which they use degenerate free integral operators. These kind of techniques are only familiar to harmonic analysis, not to PD person. So I will give up. Recently, just in this year, I gave a simple proof of their result. I proved their L2 estimate using Mullowitz energy estimate. So it's just integration by parts, very simple. But Why it's not have not been done before? Because in improving the estimate, I have to integrate the energy not just on the fixed time sleds, also on the light cone, because you know in the elementary in the partial differential equation you know the energy estimate for the wave equation. For wave equation, the energy at time t is less than energy time t equal to energy time 0, of course, but also we have energy on the cone is less than the energy on the bottom, right? So this kind of energy estimate was not used. So I using this kind of energy estimate, also not just the usual estimate, it's Mollawitz energy estimate using Mollawitz multipliers. I was able to reprove the weighted L2 estimate of Gergiev, Lindenbaum, and Zhou by just the energy estimate. So I give us elementary proof of Strauss conjecture. The other part is same. So this is a simplification. So the advantage is that we can also estimate the lifespan in the subcritical case, because we know that in the supercritical case we have global resistance, but in the subcritical case the solution blows up in finite time. But we want to give an estimate when the solution blows up in finite time. This T epsilon means the time that the solution blows up, first blows up. So we give a sharp estimate of this time that solution blows up. This kind of estimate was also, it has also have a lower bound of this type. This follows from the work of Sidderis. So this estimate is sharp. In 1979, Zhou already gave an estimate of the lifespan in case n equal to 3 and the nonlinearity is quadratic. So this was only recently done. So we give an estimate, energy estimate like this. So the estimate is like this, and then we have an CT, and naturally if we have here we have a gamma, and then U is T minus X, U bar is T plus X, and if gamma greater than 1/2, and this is C. This C is independent of T. This case is just the weighted L2 estimate of Gergiev, Lindenbaum, and Zhou. Because we do in an easy way, so we also give an estimate for gamma less than half. So CT naturally is half minus gamma. So because we are using energy estimate, we can do more than Gergiev, Lindenbaum, and Zhou. We can also consider a case that gamma is less than half. So we get an estimate of lifespan. So basic idea is just using Mollawitz energy multiply. Mollawitz multiply. So this is the Mollawitz multiply. So with Mollawitz multiply, we get a weighted L2 estimate. Also, for the wave equation, we have the weighted we have L1 L infinity estimate. So interpreting these two estimates, we get a weighted weighted LP prime estimate. So this is our estimate. And with this estimate, lifespan is easy. So it's easy to get the lifespan. So we are talking about the open problems. So the first open problem is to consider exterior problem, which means initial value problems exterior to an obstacle with, for instance, Neumann boundary, Dirichlet boundary condition or Neumann boundary condition. So in the Dirichlet boundary case, so the initial boundary value problem, so for the subcritical case, which means P greater than 1 less than PC, a student of mine and I have been able to resolve the blow up part of the problem. So for the subcritical case, it's no, but for critical and supercritical case, it's largely open, and maybe it's difficult problem, especially in the even dimensional case. This is an open problem. So for the exterior problem, this is still open problem. Also for the nonlinear Schrodinger equation, we have also similar problems. For instance, in the nonlinear Schrodinger equation, the exponent, critical exponent is 1 plus 2 over n. And for the P greater than 1 less than or equal to 1 plus 2 minus n, the blow up, the solution blow up in finite time. This was, the counterexample was given by these two, I think, Japanese mathematicians. But for the supercritical value, P greater than 1 plus 2 over n, it's still open. I have not tried. I don't know if this problem is difficult or not. So this is open problem 2. Also, we can consider Klein-Gordon equations. Klein-Gordon equation, which means for the Klein-Gordon equations, one equation is a special case. A single equation is a special case. So you consider systems. So the critical exponent is still 1 plus 2 over n. So especially, I think Strauss has studied this problem. He has something which is like a counterexample for the P less than 1 plus 2 over n. So it's a counterexample. So the aim is to prove global existence for P greater than 1 plus 2 over n. And this is also largely open. So this is some reference. Sorry, last term. Okay, thank you very much.